We're going to define and look at the equation for uniform circular motion. So first, the basic definition is honestly in the term. Uniform means the same. Circular, of course, means in a circle. And then motion means moving. And so uniform circular motion means that you are moving in the same way in a circle. And the way that we look at that in terms of same is going to be the same. Actually, I guess it's not velocity, it's same speed. And so when we are looking at uniform circular motion, we are looking at going the same speed in a circle. Now, in all of the units leading up to this, we have talked about force and acceleration, and specifically that acceleration is all about speeding up and slowing down. Okay, so why don't we kind of make a little note over here. So for acceleration, it's the change in velocity over time. Now, up until now, when we said change in velocity, we meant speeding up and slowing down, because we've been doing straight line motion. Now, notice we're keeping the same speed. Now it's the third way to accelerate, which is change direction. Velocity is a vector quantity, which means it has magnitude and it has direction. And so changing the magnitude or the speed would be speeding up and slowing down. And then changing direction is making a turn. So this part of the semester, we're finally going to stop changing magnitude, and now we're going to change direction, because a circle means changing direction. So let's see what this looks like. Why don't I give you an example? A spot that typically has a pretty bad ice situation. So this is Five Forks, and this is cold. A lot of times that area right in the middle, because of the shade and everything, can become very icy whenever it's really cold outside, come January, February time. And so let's look at this idea of circular motion using this driving scenario. So first, we're going to get rid of the ice. All right, here is my car. And I'm going to turn onto Five Forks. Now, when I do that, let's see, here's my car again, right? When I do this, I am changing direction. Since I change direction, whether or not I'm changing my speed, it means I am accelerating. If you can feel it, you are accelerating, and you can feel when a car turns. Well, this turn onto Five Forks is just a small part of a full circle. The question is which way does this force pull? Well, we know that we make the turn whenever there's no ice. If there is an ice patch, then what will the car do? Well, the car will, instead of making the turn, will go off in a straight line like this. That's the direction that the velocity will go. Therefore, in order to make the turn, it means that the force used to make this turn must go inward. And we call this centripetal force. It means center seeking. Another way you can think about it is if you were to leave like a cup or something like that. So you left your drink on top of the car, right? And if, let's see, here's the straw in your drink. There we go. If you were to make this turn, the car would turn, but the drink would not. The drink would go in a straight line. Therefore, it is being pulled, the car is being pulled inward. And so centripetal force is an inward force. Back in Newton's second law, we learned that force and acceleration go in the same direction. And so we change direction going into the circle. Because again, if the velocity is going straight outward, like we see here, right, RV, if the velocity is going straight outward, then that means we are changing our direction inward. And so here we go, acceleration. We are change direction. That's an E, inward. There we go. And so the force and the acceleration will go towards the center of the circle. All right, well, how about another example? You're doing laundry, and your washer, here's the washing machine, has a drum on the inside, that metal drum. Let's see, washer. Your clothes, whenever it goes on the spin cycle, the clothes stick to that drum. And a lot of people want to say that the reason why is because the clothes are forced outward. Well, that's not actually the case. The clothes want to travel in this direction, that straight line motion. But the drum itself, that surface, pushes the clothes in, causing it to change direction inward. So here are all of our force vectors now, all pointing towards the center of that circle. Now, there is something that does continue traveling outward. And that's the water. And this is why the spin cycle works. The clothes are held in on the drum, but the water escapes out of all of the little holes that are found around this drum. So the water continues in that straight line path. Thereby, the water is removed from the clothes. Now, the next thing is what happens with us? Like if we were, say, in a vehicle that's making the turn. Well, it doesn't feel like we're being pushed in. It really kind of feels like we're being pushed out. Or if you've ever been on one of these gravitrons, The gravitron is, like the fairs. It looks kind of like this, and you stand right here, and when it spins around, you feel like you're being pushed outward. Or the hanging swings, that's where, like you've got the chair right here, right? It's attached to the chair, and then you are sitting like this. It feels like you're being pushed outward. Well, here's what's actually happening. You are trying to move in the outward direction. So this is your movement, which is the velocity or speed. What's actually happening is the swings, this tension, is pulling you back in. The side, so there we go, the side of the gravitron is pushing you back in. But because the perspective is from you, it feels like you're being pushed outward when actually you're being held in. And we know that because if for some reason something horrible were to happen and this chain were to break, you wouldn't be pushed in anymore. Instead, you would go flying outward. That's how we know that the force is inward. Now, what is this movement, these blue arrows? What does this represent? This is your inertia. An object in motion stays in motion in a straight line. You want to move in a straight line. So, want to move in a straight line, but there is an unbalanced force that is pulling you in to the circle. And that is what we call that centripetal force. So the equation for it, Fc, that is for centripetal force. Remember, the subscript is always for the specific type. So centripetal force equals, well, mass affects force. I mean, if you have a smaller car versus a bigger car, you need a different amount of force in order to make that turn. So mass is definitely a factor. The more massive it is, the more force there has to be. This is why larger vehicles have bigger tires, so that they have more friction in order to help you keep your traction to help you turn. Well, how about taking the turn too quickly? If you take the turn too quickly, then you also go flying outward, right? You lose your traction. Therefore, that force is also related to the speed that you take your turn. The faster you go, the more traction you need. So that is also up here. In fact, speed is a huge factor. And so it's actually squared. This is why if you've got like racing tires, they're considered to be very sticky. And it's because racing vehicles need to be able to produce a lot more friction because you are going faster. So faster means you need more friction, which is that centripetal force, the ability to make that turn. The last thing is of course the circle itself. Well, if you make a very tight turn, then it means that you have a lot more force needed to make the turn. Whereas if you make a very wide, broad turn, you don't need as much force. This is why on interstates, those ramp systems and everything, like in Spaghetti Junction, they're really huge turns, is because you've got a lot more speed And so you need a bigger circle in order to reduce the amount of force needed. This is why, like, if you're on 78 and you get off on Hugh Howell, you have to slow way down in order to make that clover leaf. It's because since it's a smaller circle, you need more traction if you're still going a high speed. Well, that's opposite, isn't it? Smaller circles need more force. So that is going to be an inverse relationship. So centripetal force is directly related to the mass and velocity. So more mass needs more force, more speed needs more force. And then the circle, the size of the circle, is inversely related. Smaller circles need more force. Larger circles need less force. All right, now let's use it. I'm going to put a link up to a really awesome segment of sports science where they talk about a kickboxer, professional kickboxer, and he's actually breaking a bat with his leg. So super, super, super definitely need to check this out. Okay, so make sure that you go and look in the playlist and find the link to the sports science video. Okay. From the video, it says that he can produce 1,000 pounds of force with his leg. So what I did was I went and looked up his height, looked up his mass, and figured out, because it's his leg that's making the circle, I figured out like the proportion of a leg versus the body, figured out the proportion of mass in a leg, and that sort of thing. And so this is what I figured out for this particular kickboxer. What I want to know is whenever he provides this 1,000 pounds of force, how fast is his leg going? Well, of course, in physics, we have to use metric. And so we are going to use 1,000 pounds converted into newtons. All right, our equation, Fc equals mv squared over r. We have force, 4,448, equals 13. It's our mass. Oh, we're looking for V. And length of his leg, well, that's the radius of that circle that is made, 0.85. All right, so let's do the math. First thing I'm going to do is multiply this 0.85 over. So 4,448 times 0.85 gives us 3,780.8 equals 13 times v squared. And then next step is we're going to divide by 13. That gives us v squared is 290.83 with some more digits, but we're just going to stop there for now. We're not done. Now, to get v by itself, we have to take that square root. Now, you only take the square root if you're looking for velocity. If you're finding force, like if you're looking for the centripetal force, then you just square the velocity that's given and then you just get your answer. So the only reason why we're taking the square root here is because we have to get rid of that square. And if we do that, we get 17.05 meters per second. I looked it up, and this is over 30 miles an hour. So when he makes that kick and provides that 1,000 pounds of force, his leg is actually moving over 30 miles an hour to provide that force. It's just incredible. Absolutely incredible. All right, so what would happen to the force if his leg were twice as massive? All right, well, for that one, let's see, here we go. Let's start with the equation. Twice as massive, that's on the top, right? Twice as 2. And so it would change 2 on the top. Nothing changes on the bottom. Well, it's just 2. So if his leg were twice as massive, he would be able to provide twice as much force. What about if he was twice as tall? All right, so let's see, FC equals mv squared over r. Twice as tall, well, that's the length. So that's going to be our radius. All right, well, that's on the bottom. So 2 goes down here. Nothing changes on the top, so I guess that's 1. Yep, so it'd be half. So if he was twice as tall, he would only have to provide half the force for that same, or he would provide half the force, is what it would be. Now, for this one, the other thing you can think of is it is inversely related, and so twice is 2, which is the same as 2 over 1, and you can just flip it, and you can get half. All right, how about twice the speed? So FC equals mv squared over r. Well, twice the speed, that's up here now, and it's squared. All right, so that change in centripetal force is going to be 2 squared. So if he could make his leg move twice as fast, he could provide 4 times that force, which would be quadruple. Now, just because it's good to do an example like this, why don't we do a third of the speed? So I'm just going to go right here. So delta FC, go. If it's a third of the speed, then it'll be a third squared. That's the same as 1/3 times 1/3. So 1 times 1 is 1. 3 times 3 is 9. So if he slowed his leg down, then of course it would reduce the amount of force that he could apply, right? Because of that square, it reduces it by 1/9 of the force. All right, the last thing is centripetal acceleration. And so we said that acceleration, so acceleration is the change in velocity over time, right? So here, since we're making the circle, it's the change in direction. So centripetal acceleration is how quickly you change direction. Now, going back to our equation, right? There we go. FC equals mv squared over r. Well, way back we said that F equals ma. Well, here's m, here's m. So if we cross those m's out, then that means the acceleration is this part. So centripetal acceleration is v squared over r. If you are going faster, then you are changing your direction faster in that circle. If it is a smaller circle, then you change your direction more. So now let's use this. There's a scene from the first Toy Story where Buzz is trying to prove that he can fly. And in that one, he gets caught up on like a plane on a string. And so what I did was I looked at that scene and figured out roughly how fast he was going, roughly how long the string was. And I figured, hey, let's go ahead and find the centripetal acceleration that Buzz experienced. So we've got AC equals v squared over r. Let's see, he spins at a speed of 3.5, and that is squared. And the string is 0.42 meters long. And so if we were to put that in our calculator, let's see, 3.5 squared divided by 0.42 gives us 29.167. So we'll just do, yeah, there we go. And acceleration is meters per second squared. The way that these work with triple the radius, triple the speed is actually just like with force. And so if it's triple the radius, then we will put 3 on the bottom. So triple the radius would be a third of the acceleration, and triple the speed would be 3 squared, which is 9. And that's it.